Look at this nice algebraic problem. Here this problem is on quadratic equations. Suppose that the roots of this quadratic equation x square plus px plus q equal to 0 are rational numbers, pq are integers. We have to show that these the roots of this equation are also integers. Here the quadratic equation is x square plus px plus q equal to 0, pq are integers and the roots of these quadratic equations are supposed to be rational numbers. We have to show that the roots of these equations are also integers. These rational number, the roots of these equations are supposed to be rational numbers and these roots are also integers. We have to prove it. Here the quadratic equation is this x square plus px plus q equal to 0. This is the quadratic equation. Now we can apply the Sridhar-Charges rule to solve this quadratic equation. Primarily we can apply Sridhar-Charges rule to solve this equation. We can get the primary solution of these equations. Now by applying the rule of Sridhar-Charges, we can get the value of x as x equal to minus p plus minus root over of p square minus 4q over 2. By applying Sridhar-Charges rule for solution of quadratic equation, we have got the value of x as this. The roots of this equation are as this, that is minus p plus minus square root of p square minus 4q over 2. Now these roots are supposed to be rational numbers. These roots are supposed to be rational numbers. So the square root term, the term under square root is a perfect square, must be a perfect square. As the roots of these equations are supposed to be rational numbers, then this term, that is p square minus 4q, must be a perfect square. So p square minus 4q must be a perfect square, as the roots of these equations are supposed to be rational numbers. So the term under square root must be a perfect square. And we can assume this term, that is p square minus 4q, which must be a perfect square, and this perfect square is assumed as x square. Suppose p square minus 4q equal to x square, where x belongs to the set of integers. X belongs to the set of integers because pq are integers, so x square must be integers. X must be integers. So p square minus 4q equal to x square is assumed because p square minus 4q must be a perfect square, as the roots of this equation are supposed to be rational numbers. So this must be a perfect square, and this perfect square is assumed as x square. Now we can write p square minus x square equal to 4q. We can write p square minus x square equal to 4q. Now we can factorize the left hand side, that is which is p square minus x square. We can write p square minus x square as the product of p plus x and p minus x. That is, after factorization we get p minus x multiplied by p plus x equal to 4q. We can write 4q as the product of two of its factors in 4 ways, that is 1 multiplied by 4q, 4q multiplied by 1, 2 multiplied by 2q, 2q multiplied by 2, and also we can write this 4q as 4 multiplied by q multiplied by 4. We can write 4q as the product of its factors in 6 ways. We can write 4q as the product of its factors in 6 ways. These ways are these, that is 1 multiplied by 4q, 4q multiplied by 1, 2 multiplied by 2q, 2q multiplied by 2, 4 multiplied by q, and q multiplied by 4. Now we can choose p minus x equal to 1, p plus x equal to 4q, and also p minus x equal to 4q, p plus x equal to 1. From the second term, expression, that is 4q plus 1, we can write this, and from the third expression we can write p minus x equal to 2, p plus x equal to 2q. From the fourth expression we can write p minus x equal to 2q, p plus x equal to 2. From the fifth expression we can write p minus x equal to 4, p plus x equal to q, and also p minus x equal to q, p plus x equal to 4. Now we can add these two equations, p minus x equal to 1 and p plus x equal to 4q. By adding these two equations we get the value of p as 4q plus 1 over 2, and we can get from this by adding these two equations we can get the same result, that is plus p equal to same result, that is 4q plus 1 over 2. We can get from this, we can get the value of p from this. By adding these two equations we get p equal to q plus 1, and we can get the same value of p, that is p equal to q plus 1. From here we get, by adding these two equations we get p equal to 4 plus q over 2, and from this relation we get p equal to q plus 4 over 2. We get the values of p in terms of q from these 6 equations, and these relations are these, and here p equal to 4q plus 1 over 2. This is a fraction because 4q plus 1 is odd number, so p is a fraction. So this is not possible because p is an integer which is given, that is p is an integer which is given. P, the condition is that p and q are integers. So if this can be accepted, then p is a fraction, but p is an integer, so this cannot be possible because 4q plus 1 is odd integers. So 4q plus 1 over 2, that is 4q plus 1 cannot be divisible by 2, so p cannot be an integer. So this is not possible, this is discarded, and this is also discarded. But here this is accepted because p and q are integers. So here q, if q is integer, so p is also integer. So this relation satisfies the condition where the condition is p, q are integers. So this is accepted, this is accepted, this is accepted. But 4 plus q over 2, 4 plus q over 2, we cannot be confirmed about the integer value of p, because 4 plus q may be odd number and 4 plus q may be even number. If 4 plus q is an even number, then p will be integer, but 4 plus q, if 4 plus q is odd number, then p cannot be integer. So, this is discarded. So, this is discarded. We cannot be confirmed about the integer value of p from these two relations, because 4 plus q may be integers or may be even number or may be odd number. If even number, then p is integer, but if 4 plus q is an odd number, then p cannot be integer. So, it cannot be always accepted. So, p equal to this cannot be always accepted. So, only accepted relation is p equal to q plus 1, p equal to q plus 1, this is only accepted. So, p equal to q plus 1 is accepted. P equal to q plus 1 is accepted. Now, we can put this relation in this equation, we can get the value of x. So, we can apply p equal to q plus 1, which is got from these relations. We have got the relation p equal to q plus 1. We can apply this relation in this equation, that is x equal to this. After applying this relation, we get minus p minus q plus 1 plus minus root over of q plus 1 square minus 4q over 2. This is equal to minus q plus 1 plus minus root over of q plus 1 whole square minus 4q is equal to q minus 1 whole square. Because this is a formula, we can apply the formula, algebraic formula. This algebraic formula is a plus b whole square minus 4ab. A plus b whole square minus 4a, a means q, 4q multiplied by 1. So, we can apply this algebraic formula, a plus b whole square minus 4ab, and this expression can be written as a minus b whole square. A plus b whole square minus 4ab is equal to algebraic identity, a plus b whole square minus 4ab is equal to a minus b whole square. So, we can write q minus 1 by applying algebraic identity. We get q minus 1 whole square over 2. This is a perfect square. This is a perfect square. So, we can write minus q plus 1 plus minus q minus 1 over 2. This is equal to, if we accept plus sign, we get the value of x as minus 2 over 2, that is minus 1. If we accept the negative sign, that is minus sign, we get the value of x as minus q. This is minus q. This is. So, we have got the value of x as this and this, that is minus 1 and minus q, which are integers. So, roots of these equations are integers. So, the roots, we have proved the roots of this quadratic equation x square plus px plus q equal to 0 are integers. are these are integers. 1 is integer and q is also integer because we are given pq are integers. So, the roots of these quadratic equations are integers which are -1 and -q. So, we have proved the roots of the quadratic equation of x square plus px plus q equal to 0 are integers under the condition that pq are integers and roots of this equation are supposed to be rational numbers.